Now I have to repeat all that stuff. All right. We took a derivative. It was easy. Nice power rules. Took a nice, easy derivative. And now, to look for critical numbers, when is it 0? When is it undefined? Now, of course, look at this. When is this undefined? Never. Thank you. Again, though, I want to be in the habit of asking myself that. I don't want to forget about that option. But it's never undefined, so I won't get any of those types of critical numbers. Okay, so when is it 0? Well, of course, I set it equal to 0. I'm going to factor out a 6. Yeah, I think this factors nicely. You know, sometimes we've needed the quadratic formula quite a bit in this class, but not today, I guess. I think that factors minus 3 and plus 2. Minus 3 and plus 2, I think. Those are my factors. If I FOIL that out, that's my derivative. Anyway, now I set each factor equal to 0. I get x equals 3 and x equals negative 2. Those are my two critical numbers. Yes, Carlos?
Would there be a 0 for the 6 on the other side?
No. No, that never equals. 6 never equals 0. No. So when you set this equal to 0, you don't really set the 6. In fact, you could divide by 6 if you wanted to. It would be gone. But you don't really, or if you wanted to set the 6 equal to 0, you could ask yourself, when does 6 equal 0? You could contemplate that for a long time. And when does 6 equal 0? Anyway, never. The game of setting each factor equal to 0 is important, but the factor 6 doesn't produce any answers, right? Right. But we set each factor equal to 0. Hey, so we got a couple critical numbers. Are you guys okay? Now, so what's the deal with critical numbers? What have you learned so far today? Good. They're good candidates to be mins and maxes. That's the deal. One's probably a min, one's probably a max, I guess. And what I really want to do now is teach you how to analyze this and tell this. And now this really is in section 4.3. Here we go. This is called the first derivative test. It's hard to kind of write out all the steps. I mean, what I'm going to do is I'm just going to do a first derivative test for you and show you. But I want to maybe I should tell you what a first derivative test does. It tests your critical numbers, is what it does. It tests your critical numbers, and the conclusion is, and concludes whether they are mins, relative maxes, or neither, I suppose. Can you guys read that? If you can't read it, I did read it to you. The first derivative test is a process. It's a little process. I'm going to teach you how to do it. It's cool. And what it does is, what's it doing for you is it's going to test your critical numbers, and it's going to decide whether they're mins or maxes or neither. That's what the first derivative test does for you. Okay, so here's how you do it. You find your critical numbers, which we did, and then you put them on a number line. You make a number line. I like to label this number line F prime. I put a little label over here. It's like it's a number line where I'm going to test my first derivative. I'm testing my first derivative test. I put these critical numbers on the number line. I mean, I find these places. They're easy. You know, -2 and 3. Here's -2. 0 is somewhere in the middle. Here's 3. Are you guys okay with that? Those are my critical numbers. I put them on a number line. You know that when you put two critical numbers on a number line, it conveniently divides the number line into sort of 3 regions. Are you follow? You see that? It's sort of now divided into 3 regions. And what I want to do is I want to test each region, and I want to see if the derivative is positive or negative. So, you pick a test point in this middle region. Let's pick this middle region. Pick any test point you want in there.
0.
Good idea. 0, it's a test point. 0 is a test point. And what you do is you want to see if your derivative is positive or negative at that point. So what should I do with that 0? I should plug it into the derivative. No, I'm plugging it into the derivative. I'm testing whether the derivative is positive or negative. Where's my derivative? Here it is. Here it is. Here it is, right? I mean, here it is in factored form. Here, so anyway, anywhere you have the derivative, you can try plugging in a 0. And I really don't care what the value is, but I want to know whether it's positive or negative. It's easy up top. If you plug in a 0, what do you get? Negative 36. I don't care about the 36, but it came out negative. That means this whole region is negative. Now, 10 minutes ago, I said something important. When your derivative is negative, that means the slope of the tangent line is negative. That means the function is decreasing. We said that the other day, and I mean 10 minutes ago. And I mean, this is where it all sinks together here in this first derivative test. When we find out that the first derivative has a negative value, we know that the function is decreasing. And I write that, I denote that like this. I draw a little, the function is decreasing. I'll, you know, for this first example, I'll make these little notes too here. But in the future, I won't write that. That arrow will tell me the function is decreasing. The derivative is negative, the function is decreasing. You guys okay with that? You were convinced a few minutes ago, when the derivative is negative, the slope of the tangent line slants this way. You got to be on a decreasing part of the function. It's amazing. All right, let's test another region. Let's go past the 3. You want to pick 4? Let's pick 4. 4 is my little test point. I plug it into the derivative to test whether the derivative is positive or negative. Watch, instead of going to the top, watch you guys. When it's in factored form, it's pretty nice because you can plug the 4 in and just say, that's positive. That's positive. Positive times 6 is positive. I don't care what it is, remember? But I plugged in a 4 and said it's positive times a positive times it's positive. If the derivative is positive, the function is increasing. That little note is what tells me that. I'll just write another little note here. The function is increasing. But dude, look what I just learned. See, here's the conclusion. And I need to test this other region. But listen, here's the conclusion right here. Remember, what we were really doing was we were testing this critical point. This was a critical number. And we were trying to decide whether it was a min or a max. I think we got it. If it's decreasing and then increasing, I mean, my number line little schematic here that I'm doing is it tells me what's up. It's decreasing, it's increasing. This point must be a min. If it's decreasing and then it's increasing, I mean, look at the arrows. Just look at the damn arrows. You don't even need any math. You just need to look at the arrows. It's decreasing and then it's increasing. That point better be a min. The conclusion of the first derivative test, it concludes whether you're testing your critical numbers, you're testing around your critical numbers, and then the conclusion is that this guy is a min. I just concluded he's a relative min. Yes, Carlos?
Where you have a 0 as the test point right there. What did you say you bumped out right there?
Well, yeah, I know. I'm doing a lot here, but I took this 0 because it just represented any number in this region. I could have picked 1, I could have picked -1, I could have picked -1.5. I picked any convenient number in this region. So I picked 0 and I plugged it into the derivative and found out the derivative was negative. So I wrote a little symbol that means the derivative is negative. When the derivative is negative, the function is decreasing. So I wrote this note.
Oh, okay. So it has to do with the points that are between 3 and -2.
Right, and then I picked something in this region. You can pick anything you want to from 3 up to infinity. What did we pick? 4. You can pick any number in that region, and it would show you a positive derivative, which means the function was increasing over there. Let's try something over here on the left of negative 2. Negative 3. Anything you want. Right, you're right. Negative 3 is a test point. What do I do with that negative 3? Plug it into the derivative just to test. I'm testing the positiveness or negativeness of the derivative. Because the positiveness or negativeness of the derivative tells me whether my function is increasing or decreasing. You got to get all this language down, but you're getting it. The more I say it, I'll just keep repeating myself. But you can, if you practice talking like this, it helps. It's hard to talk like this. What am I doing? I'm testing the negative 3. Watch how I do it. In this factored form, if I plug in a negative 3, I think that's negative. And I think that's negative. And if I multiply two negatives, it's positive times 6, it's positive. I just found out that this region is positive. And therefore, hang on a second, Carlos, therefore the function is increasing. And therefore, this critical number, the result that we tested around it and found out that it's increasing and decreasing around that critical number. He's got to be a max. He's a max. That's awesome. It's very logical, but there's a lot of testing and plugging in, and you got to get the process figured out. But that's awesome. This is a big theme for this chapter. I mean, I don't mess around too long. I kind of get to the point, and I got to the point. We take derivatives, we look for critical numbers, and then we test these critical numbers because we're trying to decide if the critical numbers are mins or maxes. They're good candidates to be mins and maxes, and this is my proof of whether it's a min or a max. And sort of a byproduct, I don't know, it feels to me like the result of this test is that my critical number, I found a max, I found a min. Sort of a byproduct of that is that I also know where my function is increasing and decreasing and increasing. So I get a lot of information by doing this test. I know what the function's doing, and I know about my mins and maxes. You know what I'd like to do then, as at the end, is graph this function without my graphing calculator. In fact, we use our graphing calculators occasionally, but now you don't need them. Anybody want to throw theirs away? I'll start. Just throw these $100. Whoa, we don't need them. We should start a revolution, a mathematical revolution. All right, never mind. We might want to check our work or something. Yeah, look, what am I saying? I want to graph this function. Here, I got a little room over here. I'm going to try to graph this function. I'm going to try it without my graphing calculator. I found a couple of what I call pretty important points. This -2 and this 3 are mins and maxes. If I ask you for them, sometimes I ask you to find the mins and maxes. I ask you for a little, to list them. What are the relative mins? And I leave a blank. What are the relative maxes? I leave a blank. If there aren't any, you should tell me there aren't any. There is none, or something like that. But we found some. And if you find some, you should list them, and you should list them as a point. So who's the relative min? Which one was the relative min? That was x equals 3. Okay, but if I want the y value, then how do I get a y value, you guys? How do you always get a y value? Plug it into the original function. I mean, we've done a lot of plugging in to the derivative because we were testing the derivative. But if you're actually plotting points, you don't need to be confused. If you're plotting points, where do you plug in your point? To the original function. So I'd like to plug in a 3, please. I'm plugging in a 3 to find the y value. It could be huge. It could be, you could help me a little. 29, 54 minus 27. Negative 75? Is that right? Negative 75? Awesome. That's a min. X is 3, Y is negative 75. I just plugged it in the function, that's all. Did I do it right? Okay. Double check me, please. Hey, what about the max? We found a max? Yeah, we found a max. It happens at x equals negative 2. We found a max at x equals negative 2. I'd like the y value so I could plot it on my graph. I'd like to plug in a negative 2 to get the y value. What'd you say? 50? 50. I was getting 48, but I might be wrong. 50? 50. She plugged negative 2 in the function? 50. All right, thank you. It's not that shouldn't be too hard, but I was doing it. Thank you. All right. All right. Hey, let's see what we got. 1, 2, 3. Negative 75, look, I'm going to call that negative 75 if you don't mind. And then negative 2 and 50, which is, I'll call that 50. Oops, sorry, the point's over here. Yeah, that's an important point. That's a max, that's a min, and what's the function doing around this? You know, you can read this number line and tell what to do. Watch, you can read this number line. Starting on the left, you should increase until you hit that max. Okay, so here I am. I'm increasing until I hit a max. When I hit that max, I should decrease until I hit the min. Okay, I'm going to decrease until I hit the min. After I hit the min, I should, at 3, which happens at 3, I should increase the rest of the way. And by the way, after 3, are there any more critical numbers where it might turn around and do something? No, there aren't. I mean, you know, when we found those 2 critical numbers, those were the only 2. That's why, you know, to the right side of 3 here, we've got it figured out. It's going to just, there are no critical numbers that are going to turn it around. It's just going to increase forever here. By the way, you know, you guys, maybe you knew it was a a cubic function, and a cubic function tends to look like this. So you already maybe had a hint of what you were going for, but you're powerful here in chapter 4. You can throw away your graphing calculators and graph problems using this beautiful number line. Analyzing the derivative, what we're learning is that analyzing the derivative really tells me a heck of a lot about the function. Is that what analyzing this derivative told me about the mins and the maxes and the increasing and the decreasing of the function. Analyzing the derivative tells me so much about the function. Yes, Carlos?
Does that mean you don't want us to use our graphing calculators on the next exam?
That's not true. I'll let you have them, but I am looking. I'm looking for work. So more than just the graph, I'm looking for all the work. So I'm looking for this work. I'm looking for this work, and I want the graph. But I don't take your graphing calculators out of your hand. I don't. I let you have them. So they are helpful. As you're doing homework, it's fun to pretend you don't have them maybe for a minute. Try to get a graph of a function like this, kind of like I did, and then maybe check your graphing calculator. But yeah, that's good. Okay. Listen, there's a lot going on. When I kind of went into 4.3 with this idea, and if I go into 4.4, then there's more ideas. I can play the same game kind of with the second derivative, and I can learn about, well, we'll wait on that. I'm not going to do that. But there's more coming. Similar. I can play a similar game with the second derivative. I'll save that. I think I'll save that till Wednesday. We're getting a little low on time, but I want to do one thing before I leave. What's funny is in 4.1, Okay, I'm gonna get rid of this. So in 4.1, I'm trying to help you with your homework because it's a little strange sometimes. I think in 4.1, the big idea is find some critical numbers. The definition of a critical number, which I had up here, and how do you find critical numbers. And then they do teach you about mins and maxes, and they teach you, what they do is though, they teach you about mins and maxes on a closed interval. Now, that's okay, we can do a little bit of that homework, but I'm usually not too interested in working on a closed interval. There are some problems, some word problems where that might be interesting, but I'm more interested in what we just did. I'm looking at this whole function completely. I don't want to just look at a piece of this function. I want to look at this entire function. I want to find the relative mins and maxes. But watch this. This is what they do in 4.1. In 4.1, they say, let's look at this function on a closed interval. Okay? So I'm going to make this up. Watch this. On a closed interval from negative 3, from negative 5 to 1. I'm working on this closed interval from negative 5 to 1. And so, and what they want is the mins and maxes. And here's what they say. When you work on a closed interval from negative 5 to 1, let me just show you what that is. I'm working on this problem from negative 5 to 1. You know, there's negative 2, negative 3, negative 4, negative 5, maybe, I'm not sure. It's probably, so I'm working from negative 5, look. Maybe that point, from negative 5 to 1, watch this. To 1, here's 1, right you guys? And then that's it. The rest of this stuff doesn't even exist according to them. If you're working on this function on a closed interval, that's it. So then here's what they want you to do. Find the critical numbers, okay? Well, we did that work, right? We took the derivative, right? We found the critical numbers. What are they? Negative 2 and 3. Well, wait a minute. They are negative 2 and 3 in the big overall picture, but now they're making me work on this closed interval. So I should only pick critical numbers that live in this closed interval. Negative 5, so the 3 gets tossed away. I mean, the 3 doesn't live in there, right? Okay, so we won't even consider the 3. So my only critical number is negative 2 if I'm working on this closed interval. And then what they say is that the mins and the maxes might occur at the critical numbers, but they might occur at the endpoints of the interval, which is sort of true. I mean, look at my picture a second. Now that I've cut this, I cut the function off. It's kind of just a segment of a function. Anyway, looks like that's probably still the max. But the min might be, the min could happen at the endpoints of the interval. The mins and maxes can happen at the critical numbers, but now they say if you're working on a closed interval, the mins and maxes might occur at the endpoints of the interval. So here's what they want me to do, test all that. And they haven't taught me that first derivative test yet. So here's how you know how you test whether you want to see who's bigger and who's smaller. You want to see who's a min and who's a max. Here's what you do. You plug everybody into the original function. You plug in your negative 5. You plug in your negative 2 that you found, that's your critical number you found, and you plug in your 1. You plug in the endpoints of your interval, and you plug in the critical number you found, and you're just looking for the y values. Look, you're looking for the biggest and the lowest y values. Who's a min and who's a max. It's very logical, but it's kind of weird because you're working on a closed interval. Here I go. I'm plugging a negative 5 into the original function. I need help. By the way, let's plug a negative 2 in the original function. I already did that. That was 50. Okay, so so far that's the highest y value. It's the only y value. Let's plug negative 5 in the original function. Negative 5 in the original function. What'd you get? Negative 139. Is that what you said?
Yeah.
Awesome. So at negative 5, the answer is negative 139. I didn't really look at my picture. My picture didn't really, should have been lower, I guess. And at negative 2, it was 50. What about at 1? Please plug in a 1.
Minus 31.
Minus 31, she said. Minus 31, I think she said. Minus 31. Okay. Who's bigger and who's littler? That's all it comes down to. Who's a min and who's... I mean, the candidates now, on a closed interval, the candidates for mins and maxes are the critical points you found within that interval and the actual endpoints. And the way I'm testing them now is I'm just plugging them in to see who's bigger and who's littler. This is 4.1, special little problems on a closed interval. Anyway, I think I'd circle that and call it a min on this interval. He's the lowest y value. I'd circle that and call that a max. My picture didn't exactly look like that. Back to my picture. This should have been quite a bit steeper here. You follow me? Now the picture looks better. There's your min. There's your max. This was nothing. Something in between. Yes, Carlos.
Did you cancel out that 3 because it's not within the minimum and maximum drawn line?
Right. When I'm working on a closed interval, the 3 didn't live in there, right? So you're only working in this for these x values. Again, it's a little funny. And maybe you can tell I like working on the whole number line. But there are these problems that make me work on a closed interval. They're not my favorite problems, so you can probably tell, right? You can see just a little negativity seeping out of my lecture. But it's okay. It's okay. They're worth doing. In 4.1, they're worth doing. A few. Okay. Hey, I'm going to quit today. Thanks for listening.